Okay, thank you. So I'm going to talk briefly about internal dose coefficient, but before to start, I would like to maybe give a very short definition of what I am expecting by internal dose coefficient, just to be sure that we are talking the same language. In internal dose coefficient, you have coefficient which is easy to define. You are all scientists and you know that a coefficient is just nothing else than a value which allows us to transform one quantity into another. But we have also this term internal dose, and in fact it can be tricky to discuss about that because actually every dose to biological tissue is internal. Even the dose to the skin is in fact a dose to internal tissue. So it is definitely here a misuse of language. But what we wanted to do, and when we use internal dose coefficient, we wanted to distinguish between dose coming from external exposure, where the source is outside the body, from dose to internal exposure when the source are either inhaled or ingested in the body. So when we are talking about internal dose coefficient, we're talking about internal dosimetry, dose after intake by inhalation or by ingestion. Before to start, I also wanted to remind you that ICRP has been very active from the early beginning in the field of internal exposure. Here you've got a copy, a facsimile of the ICRP report number 2, which was about the dose, the permissible dose for internal radiation. And just remind you that this report was released in 1959, so a very long time ago. So it was really a task, a very important task for ICRP for many years. You know, everybody knows that the internal exposure to radiation are managed by the use of committed effective dose. This committed effective dose gives you a dose delivered to a body, to a tissue over time, 50 years for workers and up to 70 years for the member of public. And here you've got the definition again, the expression of this effective dose, which show you that this is the average of the male equivalent dose and female equivalent dose weighted by the weighting factor. The problem of this effective dose is that it is used for managing internal exposure, but you already know that this effective dose cannot be measured and it should be calculated. And this is where the things start to be complicated. Calculating dose after internal contamination is actually very complicated. You absolutely need to know very precisely the intake which represents the amount of the quantity which is either inhaled or ingested by the body. Once you know the intake, you should know radionuclide by radionuclide where they go in the body, because depending on where they go, they will deliver the dose in one organ or other organ, and you should know how long they stay in the organ, because the longer they stay, the larger is the dose. So the intake and deposition in tissue, just because we cannot know every intake and every deposition in tissue according to the element, the ICRP provides what we call the biokinetic model. Biokinetic model is nothing else than a box. There's the sum of boxes and arrow. And here you've got the generic biokinetic model, which show you a box which represents an organ or tissue or a group of organ, which represents the site of deposition of the radionuclides. And every box are linked together with arrow, and this arrow represents the transfer from one box to another. So for each arrow, we do have coefficient, which represent the dose rate of the flux, the rate of transfer from one box to another, and every box has its own coefficient also, which represents a percentage of radionuclides which deposit in one organ or the other. This is a generic biokinetic model, which can be very complicated, and for sake of simplicity, the ICRP has divided this in different biokinetic models. This is where we have the human alimentary tract model, which is not element-specific, which describes the behavior of element after ingestion through the alimentary tract and excretion through the feces. We do have also the human respiratory tract model, which also describes the behavior of element after inhalation. And we also do have systemic model, which describes the behavior of element after being absorbed either by inhalation or by ingestion. These systemic models are usually element-specific because it represents the interaction of every element with the different tissue, cells, and protein, and so on. Here, this is the model from ICRP, and we have a fourth model which was not built by ICRP, but which was built in cooperation with ICRP by NCRP on the wound model. It is not, I just recall you, I remind you that the wound is not part of the effective dose because we consider that wound is not a normal situation of exposure for workers. So these are the biokinetic model. Once you have this biokinetic model which describes the deposition in tissue, you should know to calculate the dose, the number of transformation in tissue. You should know by using nuclear data the energy emitted in different tissue. By using the phantoms that we have seen before and the many codes for radiation transfer, you are able to calculate the absorbed dose in tissue. Then, by using the weighting factor for radiation, you can calculate equivalent dose in tissue. And then at the end, very far end, using the weighting factor for tissue, you can calculate effective dose. So at the end, it's a very long procedure. So everything which is on the right, is given and described by dosimetric model. At the end, it's a very long procedure to calculate the effective dose after intake of radionuclides, which allow you to go from the intakes to the effective dose by using all the information which is currently described in biokinetic model and dosimetric model. You can see the number of steps which can make the process very tricky. So because of this complexity of the procedure and because it is, we should say, it is limited to some experts, the ICRP has defined new concepts and tools to allow almost everybody to perform those assessments. And we use usually two different concepts. One is the dose per intake coefficient, that I will call here DPIC, which are the formerly dose per unit intake. And the second one is the dose per content function that I will call the DPC. So what are these dose per unit coefficient? Here, if I go back to my logigram from the intake to the effective dose, what ICRP proposed is just to forget everything which is on the right of the slide and to use directly some coefficient, DPUIC, dose per unit content, which are on this form, which are given here for different type of solubility, which are given for different radioisotope, and which are just small number which take into account every information which were in the dosimetric model and the biokinetic model. So by just one step, by using the right coefficient, you can calculate the effective dose at the end just by knowing the intake and by multiplying the intake by the current and the right coefficient. So it is completely, it's very easy to use and definitely easier than the former method using all this dosimetric and biokinetic model. So these are some examples of dose per intake coefficient which are provided by ICRP. This is something which is taken from ICRP publication 134, which was published last year. Here, this is a table which provides a committed effective dose coefficient in sievert per becquerel for the inhalation or ingestion. Here we've got the example of 3 isotopes of strontium, and you can see that from these tables that we have information for different type of different solubility of compound after inhalation and different solubility of compound after ingestion for the 3 isotopes, and so you have different coefficient. So this was an example for the strontium, but I should say that ICRP will provide those coefficients for inhalation and ingestion of the most important isotope and for almost every element. Now, it can be sometimes, you can have sometimes where you have no idea of the intake when you have some worker who comes to you with some contamination and for whom you have no idea of the intake. In that case, you may have some access of what we call the bioassay, which are the measurement of the radioactivity either in the lung or in the body or in the feces or in the urine. So once you have this bioassay, what ICRP proposes is to use directly the information of the radioactivity in the bioassay by using the DPC function, the dose per content function, to derive directly the effective dose. So again, ICRP provides this kind of table which show you, this is an example for zirconium-95, but again we've got table for every important isotope, and this table allows you to, according to the time after the intake, according to the solubility of the compound. If you have a compound of high solubility or very slow solubility, you can decide to use one coefficient or one other coefficient to directly derive the effective dose from the knowledge of the activity in different parts of the body. Here we have total body, lungs, and urine, etc. So this system, which is really easy to use, replaces the former system that most of you already know, which by the past, you remember, you were obliged to go from the bioassay to the intake using retention function, and then from the intake to the effective dose using the dose per unit intake or the dose per unit content. So we wanted to simplify the system because here in this system we had two steps, and two steps it's two possibility of mistakes. So one wanted to really resolve and solve the system and simplify the system in only one step just to minimize the risk of error. So anyway, because ICRP is very nice, we provide anyway the former reference bioassay function, which allow you at every time every time after the intake to allow and to determine the activity per intake, knowing the activity in different bioassay. So this is not new, and ICRP has worked many years for that and has provided information on dose coefficient for worker as for member of public. You all remember that the publication 30 series, which start in 1979, which provide dose coefficient for inhalation and ingestion on many radionuclides. This publication 30 series was completed by publication 68, with updated dose coefficient, and was also completed by the publication 54 and 78, providing some guidance on the design of monitoring program and the interpretation of result. So this was former publication. For the member of public, in the similar way, we had the publication 56 series, which provides the age-specific dose coefficient for inhalation and ingestion of 19.1 element using up-to-date model and the latest ICRP publication. And we also still have a publication 88 and 95, which were about dose to embryo, fetus, and infant. The problem is that science, we have made many progress in science during this period. You remember that the first dose coefficient for the worker were published almost 35, 40 years ago. We have made progress in physiology and biokinetic model. We have published new data on reference man. We have a new alimentary tract model, so I will not detail the model, but just to remind you that the former model had only 4 compartments, and that the new model, which is definitely much more sophisticated, allow us to better describe the deposition and the retention of the different radionuclides in the different tissue, including the wall of the tissue. So just to show you that the science is progressing, and we are trying to integrate the science and the new development of science in this model. We do have also new element-specific systemic model, which are more physiologically realistic, which better describe the real behavior of the element. Again, I will not show you too many examples, but just for a picture, a snapshot, this was the former model for iodine, which was a very easy, simplest model with three compartments. And here, this is a new model for iodine, which describe, we hope, more precisely the behavior of the iodine in the body. The same applies for the strontium. With the former model, strontium is known to deposit on the bone, and so we had few compartments in the bone, and here, definitely in the new model, we try to describe more precisely the deposition of the strontium in the different compartments of the bone and in the different compartments of the body. We also have a more realistic treatment of the biokinetic of the radionuclide daughter, which are now treated independently from the parent. And we also developed new data supporting update of the human respiratory tract model. So I will not develop the difference between the old model and the new model, mainly because they have been developed and they have been exposed many times during the past previous public presentation. But just I would like maybe to focus on one point. On what we call the default parameter value, you remember that for inhalation we distinguish the compounds which are highly soluble from compounds which are not very soluble, which are here from type MS, and we define some coefficient which are the rapid fraction and the rapid rate and slow rate. And here, just to emphasize the fact that we have changed a little bit some coefficient to better represent the reality and to better represent the new result for science. And one thing which is also important is that in the new human respiratory tract model, we allow to have element-specific value for some data, which really try to better fit to the reality of what we see, what we observe in the experience. And this is why, for example, for the uranium absorption, we try to be as specific as we may. Here, for example, for uranium absorption, we have default type F, we have default type M, and default type S, but we also have for some specific compounds, such as here uranyl nitrate or uranium peroxide hydrate, etc. We have specific data just because we consider that we had in the literature enough data to derive specific parameters for this specific element. And this is really a progress compared to the previous model where we had more, I would say, default value compared to the default value story. We also had many progress in terms of dosimetry and monitoring. We have heard before the break of the development of adult reference computational phantom, so I will not come back on that. We had also in the last ICRP recommendation, in ICRP 103, the adoption of this realistic phantom, the change of weighting factor, change in calculation of equivalent doses, etc. And every progress made during this last period really lead us to provide provision, to revise the previous coefficient and to give a provision of new dose coefficient with guidance on monitoring program and data interpretation. So the work we have done is divided in two parts. We have one part which is called OIR for occupational intake of radionuclides, which correspond to a revision of model and dose coefficient for worker, and the second part, which is for environmental intake of radionuclides, which is about the revision of model and dose coefficient for the member of the public. The OIR part 1 has already been published. It's ICRP publication 130. It's really a description of how to control the occupational exposure to radionuclides, a description of the generic biokinetic and dosimetric model, description of the methods for individual and workplace monitoring, description of monitoring program, plus description of general aspect of retrospective dose assessment. And the OIR part 2 to 5 are really about the elements, every element. So for each element section, we have a description of the chemical form in the workplace. We have a description of the main radioisotope, which are interested for radiological protection. We have, and that was a very large part, which really took us years to complete, was to review the data on inhalation, ingestion, and systemic biokinetics. We have provided the structure of new biokinetic model and parameter value, and we also describe the monitoring techniques for each element and the typical detection limit. And then we provide the dose coefficient, the reference bioassay function, and the dose per content function in either printed document. The printed document is already, for each part, is 400 pages, so it's a very thick document. So we decide to also provide the every data you can need in electronic annexes. So where we are now, OIR part 2 containing the important element for radiological protection is already published. OIR part 3 containing also other elements important for radiological protection is currently in press. We plan to publish, to provide the OIR part 4, which will provide those coefficients for the lanthanide and transuranic element next year, and OIR part 5, that will treat every other element, will be provided in 2 years, hopefully 2 years from now. This OIR series so provide information plus dose coefficient, but they are also provide together with a data viewer that will allow you to directly have the information you need in terms of dose coefficient, reference bioassay function, or anything else during this software, which is kindly provided by Vlad and colleagues. So you can see, you can find that everything in the ICRP website. Similarly, for the ICRP, for the environmental intake series, we are doing exactly the same job. We have divided the work in 4 parts. The part 1, which is in progress, will provide the same information than for the worker, but it is here for the member of public, so including the age-dependent parameter. So they will be provided for every element. Part 1 will be about every element which are currently covered in OIR part 2, 3, and 4. Part 2 will be for the other element, and parts 3 and 4 will be for the breastfeeding infant, maternal dose, and in utero internal dose coefficient. So I'm pretty short in time, so I just would like to show you and maybe to try to answer to a question that everybody asks, which is what difference does that make between the former model and the new model? And this is just two diagrams, two pictures to show you that in fact the difference are very small in term. And here you've got in blue the former dose coefficient for some element, in red the new coefficient. So definitely the new coefficient we have more dose coefficient for in ICRP 134 because we treat more situation, but you can see here that the difference between the old coefficient and the new coefficient is very small. And this is only just due because the former system was already good, and so we did not overestimate too much or underestimate too much by the past the dose delivered to the worker because the system was already nice. So here we have a very sophisticated biokinetic model and dosimetric model which provide you more assurance in terms of dose coefficient, but which does not change too much. The maybe only difference that we can have here is really a small difference concerning 2 or 3 elements, 2 or 3 radioisotope. It's concerning here the lead 212, the lead 214, and the thorium. We have here in that case an increase of the new dose coefficient compared to the previous dose coefficient by a factor between 4 to 8. And this is just due to different hypotheses that we have taken. For the lead, for example, we have included the idea that the lead can be bound in the respiratory tract. And for the thorium here, we have the good reason to think that thorium may be dissolved more slowly than it was planned before. And this is why it increased a little bit the dose compared to the previous intake, to the previous dose coefficient. But overall, at the end, the difference are really tiny. So I'm pretty finished. Sorry for being a little bit late. I just wanted to thank my colleagues because you can imagine the enormous amount of work that is behind this. It's nice to provide those coefficients, but including, I mean, it's really an enormous amount of work which has started 15 years ago almost, and so a really great thanks to all these people. Thank you to you.